Hi, my name is Kathryn Luczek, and I just finished my first year of study at the University of Michigan. This summer, I had the opportunity to work with Dr. Jason Gilbert in the Atmospheric, Oceanic, and Space Sciences Department at the University of Michigan on a project involving the replacement of nanogratings for carbon foils in space-based mass spectrometers. I'd like to first introduce you to MESSENGER. It's the Mercury Surface Space Environment Geochemistry and Ranging Spacecraft. It is launched by NASA in 2004, and this past March, it started its orbit around Mercury. On board MESSENGER is a plasma instrument package, and this involves a fast-imaging plasma spectrometer, also known as FIPS. FIPS analyzes the ion composition of solar wind and Mercury's atmosphere. It was created at the University of Michigan, and as far as mass spectrometry devices go in space, it is the smallest and lightest when it was created. Mass spectrometry in general is this, as you see here, it's composed of two different parts, the electrostatic analyzer, or ESA, and the time of flight section, or TOF. As ions enter from the left of the image, the ESA uses adjustable voltages to separate the ions by their energy to charge ratio, and also filters the UV light. As they go past that section, they go through a carbon foil, which emits electrons, which trigger the first time of flight sensor, and then the ions will hit the back of the time of flight section and hit another sensor, and they can therefore measure the velocity of those ions. And that velocity, as well as the energy to charge ratio, allows us to calculate mass per charge, and that way we can figure out what the different ions are. So what I'm trying to do is figure out if we can replace the carbon foil in those mass spectrometers with nanogratings. And if nanogratings can allow ions to pass through, filter UV light, and trigger the time of flight section, then space-based mass spectrometers will be even smaller and lighter than FIPS because we'll be able to remove part of the ESA section. And that will allow us to do more missions with these mass spectrometers. So what I did was set up I had a particle accelerator, and then the motion stage, which is seen on the right, which has a plate, and that has two holes in it so the ions can pass through, and it moves up and down such that I can find the ion beam very easily. And there's also a sensor in the back of the chamber that senses the ions. What I had to do first was to calibrate the particle accelerator with different currents and voltages such that I could figure out the areas which had the highest count rates between 1 and 12 kiloelectron volts and 2.9 and 4.2 amps. Then I could use those different energies in order to get the best data on the nanogratings. So the nanogratings I was testing were the freestanding silicon nanogratings. You can see that they are, on the right, you can see the nanogratings themselves. They have 2 micrometer and 5 micrometer nanogratings, and then they are set on a 1 millimeter separation of the base structure. You can see that in the black lines on the pictures on the left. And the separation structure is quite a bit bigger than the nanogratings themselves, so we did our best to center them so that we can get the most nanogratings around the holes. Because the first thing I did was a comparison between two holes, one being open in the bottom on the top, and the one on the bottom being covered with a nanograting. And that way I could compare the rates of the ion transmission through the nanograting and the open hole. This was done with hydrogen and carbon ions, and from a -12 to +12 degree angle and at 1 kiloelectron volt. I also did a test with charge exchange. Compared the rates using deflection plates, which are found inside of the chamber, to figure out the amount of charged ions versus the amount of neutrals, and those would be separated by the deflection plates. This was done with hydrogen and carbon at a 0 degree angle and from 1 to 10 kiloelectron volts. So as far as my preliminary results go, thus far we've been able to do transmission testing with a 2 micrometer nanograting from 1 to 10 kiloelectron volts at a 0 degree angle and without any deflection. And we found on average the hydrogen ions have a 40% transmission and the carbon ions have a 50% transmission, which is very promising for using nanogratings instead of carbon foils. So in the future, I still have to do a 2 micrometer nanograting charge exchange test, a 5 micrometer nanograting transmission and charge exchange test, as well as do the analysis of those. But based on the information we have right now, it looks very promising that we'll be able to use nanogratings instead of carbon foils in space-based mass spectrometers.